All right, today we have 8.5, which are logarithmic functions. Okay, so on to something brand new today. Our objectives, we're going to convert between exponential and logarithmic forms. Okay, so we've been working a lot on exponential. We're going to evaluate logarithmic expressions and graph logarithmic functions. Okay, so first up, logarithmic functions are inverses of exponential functions. So they're the inverse. Okay, remember multiplication and division are inverse. Addition and subtraction are inverse. So logarithmic functions are simply the inverse of exponential functions. Okay, so if we consider the exponential function of y equals 2 to the power of x and its inverse function, x equals 2 to the power of y. The inverse of a function is found by exchanging the x and y variables. That's all we've done here is exchange the x and the y. The graph of the inverse is the reflection of the function's graph in the line y equals x. So all we've done here is we just have a graph of this. So we have the two tables, one of the first function, y equals 2 to the power of x, and then the inverse, x equals 2 to the power of y. Okay, and we're they're just filled out. You can see that all we've done here is the x and the y, and they've just flipped them. Okay, they changed their places over here. And this is that, it said it's a reflection here across that y equals x line. And it is. This is the y equals 2 to the power of x function, and this is x equals 2 to the power of y. Okay, so we're looking at them, trying to understand that they are inverses of each other. All right. Previously, we had no method of solving for y in x equals 2 to the power of y. The logarithmic function allows us to solve such an equation now because it's the inverse. Now we can solve it. Okay, so a logarithmic function. Let's look there because it's pretty exciting stuff. If my paper would move, it's like stuck on me. Okay, better. Anyway, a logarithmic function. So we're assuming b and x are positive numbers and b is not 1. Okay, then I should have made this bolder. Y equals the log of x with a base b. If and only if x is equal to b to the power of y. Okay, so let's look at this. So here we go. This is our logarithmic function, though. It's going to have log in it. And it says the notation here, we might say y equals log bx. It's not actually how you read it. It's read as y equals the logarithm of x in base b. Okay, so y equals the logarithm of x in base b. So the logarithm of a number is the exponent when the number is expressed as a power of b. So let's think about that again. The logarithm of a number is the exponent. So the logarithm of a number, the logarithm is the exponent when the number is expressed as a power of b. All right, so let's look at this. We have log. What is the log of 8 in base 2 equals 3? Because 8 equals 2 to the power of 3. Okay, so the log of the number is the exponent. Okay, so see, the log of the number is the exponent when the number is expressed as a power of b in the base. So this was my base, and now, okay, it's my base here. So it was the log, it was my subscript 2, and now it's my base in the exponent. Or here we have the log of 1/9 in base 3 equals -2 because 1/9 is equal to 3 raised to the -2 power. Okay, so I'm pulling out this number is my base, this number becomes my exponent. Okay, so here we have this great chart that gives us a comparison so we can go back and forth between exponential form and logarithmic form. So exponential is x equals b to the power of y. The logarithmic form is y equals the log of b, or log of x in base b. Pardon me. So you'll need those to quickly convert between logarithmic and exponential forms of an equation. Okay, so let me move this on up so we can get examples 1 and 2 kind of on the same screen and things, and keep that. There we go. That'll be nice. Okay, so example 1, we're converting to exponential form. So we have them in logarithmic form. We just want to convert them to exponential form. So remember, this number becomes our base. Okay, this number becomes the exponent. So 5 to the third is equal to 125. That is exponential form. So here in B, we've got our base, our exponent, and it's equal to the last number there. That was the same way over here too, is equal to 125. Okay, in log of 0.01, the log of 0.01 in base 10, 10 is my base, my exponent is -2, and that equals 0.01. So that's all we're doing, is rewriting them in a different form. So in example 2, we're going to convert from the log to the logarithmic form. Pardon me. So we're given exponential, and we're going to convert it to logarithmic. So I'm going to say log. Okay, what was my base here? Okay, my base is 2, so this is going to be log 2, or log base 2. Okay, we know the 4 then is going to go over here, and the 16, my answer goes here. So the log of 16 with a base of 2 equals 4. All right, so here we're going to go log, and what's my base? 10 is the base, right? So it's log. I'm going to put the 10 down here, and this is 1 equals 0. So the 10 and the 0 can never go on the same side. But if you remember, this is your base of the exponent, so it's going to drop down on your log. You're going to be in great shape. On this one, we're going to do log. And what's my base of this exponent? It's the 2. So I'm going to do log with the little 2. And then the 1/8. So the log of 1/8 in the base 2 equals -3. And that's it for that. Just using these formulas to remember to go back and forth. And what's going to help you is, again, remembering like, okay, if this is my little number, here the log and the number that's there, it's telling me in base. That becomes my base in exponential form. And I think that's a big thing. Like, that's going to help you tremendously. All right, let's look at example 3 and evaluate log of 1 over 81 in base 3. Okay, so I'm going to take this log and I'm going to set it equal to y. Okay, so I'm going to take this equation. So I'm going to take log of 1 over 81 in base 3, there we go, and set it equal to y. All right, that's going to help me. Maybe I should, now that I have an equation, like all of these were equations, I can set it equal, I can convert it to exponential form. Okay, so in exponential form, let me change my colors here. Okay, I've got this little 3, so that's going to become my base. So 3 to the power of y is going to equal 1 over 81. Okay, so then, okay, it's telling me that I need a base 3 here, right? Like everything, this number needs to be expressed with a base of 3. Okay, so I need to take this 1 over 81. Let's do some division by primes here. So I'm going to divide by 3. That gives me 27. Divided by 3 gives me 9. Divided by 3 gives me 3. Okay, so maybe you'll remember that. So 3 to the y is actually equal to 3, or let me back up. I don't want to get too far ahead of myself. Is equal to 1 over 3 to the 4th power. Okay, well that doesn't help me as a fraction form, but remember, if I want to get this this to my numerator, I just need to give it a negative exponent. So 3 to the y is going to equal 3 to the negative 4th power. All right. Then, when I have the same bases, because I have the same bases, I can apply that property of equality of exponents. And that means that y then equals negative 4. Okay, and that therefore means, hopefully, do you know the therefore symbol from logic? Okay, therefore, the log of 1 over 81 in base 3 equals negative 4. That is actually our final answer right there. Pretty sweet stuff, right? So again, logarithms and exponential functions are inverses of each other. That's where we're really taking away today and how to solve them. Okay, so example 4, we're going to evaluate some more problems. Hopefully these are maybe a little bit simpler for us. Okay, so the first step was to set it equal to y, and then we can put it in exponential form. Okay, so now we're going to say 2 to the power of y equals 8. That's kind of hard to see the y. Okay, then we've got to write y as we have to write 8 with a base of 2. So 2 to the power of y equals 2 cubed. So then y equals 3. I kind of shorted myself some room here. I'll get them all to fit. Okay, on this next one, the log of 25 in base 5 is equal to y. So we're going to say 5 to the power of y equals 25. And we need to express 25 with a base of 5. So 5y equals 5 squared. And then that property of equality says that then, okay, well, y has to equal 2. Okay, in log of 1/4 of the number 1/4 in base 2. So we're going to have, we have to set it equal to y first. So we're going to have 2 to the power of y equals 1/4. Okay, we need to express 1/4 as a power of 2. So the 4. So this is going to be 2 to the power of y equals 1 over 2 squared, which would be 2 to the power of y equals 2 to the negative 2, right? So y equals negative 2. And our last one, log of 3 in the base of 9. We're going to set it equal to y. So we're going to have 9 to the power of y equals 3. Okay, yeah, that's right. I was just thinking, like, how am I going to express 3 as a base of 9? That is weird. Okay, so 3 as a base of 9, if we think about that, is going to be, let's see, 3 to the base of 9. It'd be this, because the square root of 9 equals 3, and the square root would be 9 to the 1/2 power, would equal 3. Okay, so 9 to the power of y is equal to 9 to the 1/2 power. So y equals 1/2. There. Sorry, it took me a second to process through that in my head. Should have given myself a little bit more room for those notes. My apologies. Okay, so recognizing the inverse nature of exponential and logarithmic functions helps us quickly simplify expressions. Okay, so recognizing the inverse part. So we have log of b to the power of x in base b is equal to x. Okay, so these numbers canceled out, kind of, it looks like, right? And they just left us with x. Woo, if I could talk. But we can also have this b, okay, is our base, and raise it to this exponent of log b, the log of x in base b, and that's equal to x. Okay, so they're both equal to x. Base 10 logarithms are frequently used because we use a decimal number system. And a decimal number system, right, is a base 10 system. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now we have 2 digits. Okay, so we live in a base 10 system. These common logarithms are usually written without the subscript of 10. So notice there's no 10 down here. We write it without that, but it means the exact same thing. They're just considered common logs. So the log of x is equal to the log of x in the base 10. All right, so example 5, you can use a calculator to evaluate each common log. You're going to round to the nearest 10,000th if necessary. So we're going to use the log button on your calculator. So I'm going to set it here too. Maybe you can see it. Okay. Maybe I should clear some of this handwriting off. Okay. Let's see. Okay, so we're looking at this log base, these common logarithms. Okay, so all we're going to do here is we're going to hit log of 100, close those parentheses, and we get 2. Our answer is 2. That equals 2. We're just using that. Okay, because again, let me make this make sense. It's the log of 100 in the base of 10. So 10 squared would equal 100. Or if we had, so that's why it's a 2 there. Or if I went back and said this is equal to y, maybe I should take those same steps. Okay, so 10 to the power of y equals 100. Well, we need to write 100 with a base of 10. So 10 to the power of y equals 10 squared. So y equals 2 here. Okay, and then I also have there that you can use second log to check your answer. So here your answer is 2. So what you're going to do is you're going to do second and log, because it gets you that 10 or whatever there. And so you put the 2 in there and hit enter, and you get the 100 back that you put in. Okay, so let's try the next one. It's log of 1/1000th. So we're going to do log of 1 divided by 1,000, because fractions are division, or you could put in the fraction, either one. And we're going to get out that it equals -3. Okay, and again, we can check that. So we're going to do second log. And if you notice above that, it says 10 to the power of whatever, or x. So we're going to put in our answer, the -3. And our answer is 1/1000. So we know we're solving it correctly. Okay, then how about log of 30? So we're just doing log of 30 is 1.4771, even. Okay, so if I want to check that, I'm going to do second log 1.47712. Okay, so that came back at 29.999, right? So it's about 30, because we rounded, so the calculator's going to round. And our last one is the log of 0.3. So log of 0.3, or 3/10, is negative 0.52287. So negative 0.55228. We'll say 8, because it's rounding. Okay, excellent. Okay, so it's like, whew, you definitely need a scientific calculator to be able to use some of those logarithms and calculate them. So those are called common logs. Remember, they just don't have the base, they don't have that 10 down there. They don't write that subscript of 10, because they're in the base 10 system. All right, so I want you to recall, think back, that exponential functions in the form of y equals b to the power of x have a domain of all real numbers, and they have a range of y such that y is greater than 0. Okay. Since logarithmic functions, y equals the log of x in base b, are inverses of these exponential functions, they have inverse domain and ranges. So their range is now x, such that x is greater than 0. So this is the inverse. Our x and our y's swapped, right, for domain and range. And our range is all real numbers. So here the domain and the range have traded places, but their values are the same. So when these exponential functions are reflected across the line, y equals x, so, right, this line right here, that's that y equals x. Their horizontal asymptote becomes the vertical asymptote, y equals 0, of the logarithmic functions. Okay, so so for this first one, y equals b to the power of x, we had a horizontal asymptote. Okay, so now when they reflect, the asymptote becomes a vertical. This is a vertical asymptote for the logarithm, and this is the y equals 0 line. Okay. All right. So example 6 says graph each logarithmic function. Let me clear this and move it up a little bit. Okay, so we're going to graph each logarithmic function for example 6. Well, the easiest way to do this, okay, is let's look at these actually. We have y equals the log of x in base 3, and y equals the log of x in base 1/3. So let's make a table and pick some values for x that would work well. So we have 3 and 1/3, so we could use 1/9, 1/3, 1, 3, and 9. Okay, and so in the first one, let's change up our colors a little bit. Okay, I do have red. Let's do our log of x in base 3 here. So to solve that, we've got, remember, we're going to say this is equal to y. So we're going to have 3 to the power of y equals x, and our x is 1/9. So we're going to say 3 to the power of y equals 1/9. Okay, so we want to express this with a base of 3. So we have 3, yeah, I guess I'll leave it that way. We'll do this one out really far. 3y equals 1/3 squared. So then 3 to the y equals 3 to the -2. So y equals -2 here. Whew. All right, so that's going to take up a ton of space in my chart. So let me actually erase all this. I wanted to make sure you saw it. And maybe I'll do my work out here instead in some scrap area. Okay, so we've got -2 here. And then, so for 1/3, we're going to have 3 to the power of y equals x. Still, but this time our x is 1/3. So we've got 3 to the power of y equals 1/3. 1/3 is to the power of 1 here, right? So this is going to be 3 to the -1. So y equals -1. And I'm trying to find a shortcut way to show my work. Hopefully that's making sense to you. So now our x is 1. So we've got 3 to the power of y equals 1. Okay, sorry. So we have 3 to the power of y equals 1. Well, any number to the power of 0 is equal to 1. So 3 to the power of y equals 3 to the power of 0. So our y equals 0 here. Okay, let me move all this. It's getting in my way. One day I'll get it figured out. Okay, so we've still got 3 to the power of y equals x. All right, this time x is 3. So 3 to the power of y equals 3. Okay, well this is 3 to the power of 1. So our y is 1. And our next one, we have 3 to the power of y equals 9. Okay, well 9 is equal to 3 squared, so y is equal to 2 here. All right, so, and we're supposed to graph this. So let me go ahead and graph my red equation here. So I've got 1/9 and -2. So 1/9 I'm barely going over, and then I've got -2. So it's like right there. 1/3 is -1. 1 is 0. 3, 1, 2, 3 is 1. And 9, so this is 3, 4, 5, 6, 7, 8, 9 is 2. All right, so here is my first problem there. Okay, so that log base 3 of x, or y equals. I should do that. Okay, now let me change it up, and we'll do b. Our y equals log of x in base 1/3. Okay, so in this case, our equation is going to be 1/3 to the power of y equals x. Yikes. Right, so now we got to get them in 1/3 bases. Okay, so our x is 1/9, so we're going to have 1/3 y equals 1/9. Okay, and we want this in a base of 3, so that's going to equal 1/3 squared. And that's equivalent to 1/3 squared, because 1 squared is 1 and 3 squared is 9. So y equals 2 here. All right, for our next one, we have 1/3 y equals 1/3. Okay, well this is to the exponent or the power of 1. So we've got 1 for the next one. That one's pretty good. Then we've got 1/3 to the power of y is equal to 1, because our x is 1. Okay, again, any number to the power of 0 equals 1. So we can take 1/3 to the power of 0, and that equals 1. So our y equals 0. Again. Okay, for the next one, 1/3 to the power of y equals 3. Okay, so we need to get this as an exponent of 3, or as 1/3. So 1/3, okay, so we would need to, let me think about this. We want to put this in the denominator, so that would equal 1/3 to the -1 power, okay, which would be equivalent to 1/3 to the -1 power. Okay, so in this case, if that was the case, it would put the 1 in the denominator and the 3 in the numerator, and we'd be back equal to 3. So just checking here, doing some work. So y is equal to -1 here. All right, I'm going to have to erase and get some room. All right, so our last one. These fraction and whole numbers, they're tricky, right? So we've got 1/3 to the power of y is equal to our x. Our x is 9 this time. Okay, so we've got to express that as a fraction of 1/3. So 9 would be 1/9 to the -1, if you recall. Okay, and then 9 would be 3 squared. So this is equal to 1/3 squared to the -1 power. Okay, when we have a power times a power, we multiply them. So this is 1/3 to the -2. Okay, so this is equivalent to 1/3 to the -2 power. Because again, 1 to the -2 would put the 1 in the denominator, squared, and move the 3 to the numerator, and it's squared. 3 squared would be 9, 1 squared would be 1, so we still end up with a 9. So 1/3 to the power of y, y is equal to -2. There's a lot of work there, right? A lot of work. So let's graph this one. We've got 1/9 and a +2. So 1/9 and a +2. 1/3 and a +1. 1 and 0. 3 and -1. And 9 and -2. Okay, and so this is our y equals log of x in the base of 1/3. Whew, that required some mental math and pulling out some old strategies. Okay, very nice. We've got one more problem on the next page. I know it's a long set of notes today, but we're probably going to spend some extra time on it in class. Okay, so this last one is the graph of y equals log of x in base b has an x-intercept. Okay, you probably noticed it earlier, but it had an x-intercept of 1, 0 and a vertical asymptote at x equals 0. So it had that vertical asymptote, which is the y equals 0, or x equals 0, which is the y-axis. The graph will contain the points, will always contain the points b, comma 1, and 1/b, comma -1. So that's kind of helpful. We didn't know that earlier, but kind of learned it. Now, let's look at something else. Equations of the form y equals a log subscript b of the quantity x minus h plus k, whew, it's a tongue twister, can be graphed using the same transformations of the parent function, which is y equals log of x in base b, that were used for our quadratic and our exponential functions. Okay, we're using those same ideas. Okay, so what that means is if we're going to look at this, okay, and see this, we know that the a, that first number, is going to stretch or reduce. It's going to make it bigger or smaller. This is a +3, so this is going to stretch or enlarge. Well, let's stick with stretch. It's going to stretch the graph. It's going to stretch the graph, okay, by a factor of 3. Okay, then hopefully you remember that the 4 here, okay, this 4, okay, is that horizontal or vertical? Do you remember? Okay, if it's h in the equation, it's horizontal. Okay, so this is a horizontal change. Okay, it was negative here, so that means this is actually -4, because it would be x minus -4. So how is that going to move it horizontally? Okay, so it's going to shift it 4 left, okay, from the parent. And we don't have a k. We don't have anything else out here plus anything. So we're not moving it up or down at all. We're just shifting it, stretching it, and shifting it to the left. Okay, so if we were to graph the parent function, I should have moved this up a little bit, but we'll make it. Okay, so if we graph that parent function, y equals log of x in base b. Okay, it told us we're going to have points at b1 and 1/b -1. But let's pick some points out here for our chart. Let's see. Let's pick some x values that we want to use. Let's use we've got a 3 here, so maybe we should do a 3. I'm trying to think what I should use for x values. It says we're going to have, or let's see, we've got a log 2. So actually, because that's our b, right, our b is here, so let's use 2, and we'll use 1/2 for sure. So let's do 1/2, and 1 and 2, and maybe we should do 4. 1. Let's do 4. My screen's a little hard to see. Let me move my screen here. Oh, nope. There it is. Let me move my screen down a little bit so we could get my 4 in there. Okay. And I'll squeeze a 4 in there. Okay. So, if we've got this, that means we're going to have b to the power of y is going to equal our x, right? B to the power of y equals x, and so our x is here. So we're going to have b to the power of y equals 1/2. How am I thinking about this? I am a goofball. I don't know what I was thinking. Log bay of x base b is in this part, not the actual problem. I was like, wait a minute. I like froze on the spot up here. I could delete it, erase and delete, but you guys, it's good for you to know that I make mistakes too, right? I'm by no means perfect. So let's go back to this. We're going to use that parent function of y equals the log of x in the base 2 system. So 2 to the power of y is going to equal our x. Yikes, that's so much better. Okay, so we've got 2y equals 1/2. Okay, so this is kind of that same process we did earlier. We want to write it as a power, as a base of 2. So we're going to move this up. So we need to apply a -1 exponent to move it up. So this is 2 to the -1. So y equals -1 here, which is what it said it was going to have, right? 1 over b, that's our 1 over 2, is going to equal -1. I kind of could have looked there, but I didn't. I want to show it to you. So 2 over y equals 1. Okay, we want to write it as a base of 2. We know 2 to the power of 0 equals 1, so y here equals 0. 2 to the power of y equals 2, so that's 2 to the power of 1, right? So y equals 1 here. And 2 to the power of y equals 4. We want to rewrite 4 with a base of 2. So that's 2 squared, so y equals 2. So if I graph that, I've got 1/2, -1, and 1, 0, 2, 1, and 4, 1, 2, 3, 4, 1, 2. Okay, so notice our asymptote is that vertical axis, that y-axis. Okay, see if I can change my color. Okay, it's still recording, good. But that's kind of in my way. Let me see if I can, nope, that's not what I want to move. Well, there we go. It moved back up to the top. All right, so for the next one, okay, I'm going to, actually I don't need to do the next one. Thank goodness, right? Because it's stretched by a factor of 3, and I'm moving it 4 to the left. Okay, so let's look at that, what that means. To stretch it by a factor of 3. So instead of having -1, 1/2 -1, I'm going to stretch that, and I would have a -3. I thought I changed to red, but I didn't. Okay, it won't let me. And then 0 times, so we're just multiplying by 3 here, right? To stretch this. So 0 times 3 is still 0. 1 times 3 is 1. And 2 times 3 is 6. Okay, so I'm going to have 1/2 -3. So I'm going to have 1/2, and it's going to be -3. 1, 2, 3. But I also have to move it left. So don't forget the left 4 to the left. So 1, 2, 3, and then 4 left. 1, 2, 3, 4. Okay, so I'm going to take this one. It should be 1, 0, but I'm going to move it 4 over. 1, 2, 3, 4. Then I've got my 1 times 3 is 3, not 1. So here I'm going to go up to 3 because it's 2, 3. So 2, 1, 2, 3, and now I'm going to move it left 4. 1, 2, 3, 4. And then the next point is 4 and 6. I've stretched it. So 4, 1, 2, 3, 4, 5, 6, and I need to move it left 4. 1, 2, 3, 4. Okay, so now this is my new one. This is that 3 log of the quantity x plus 4 in base 2. Okay, where is the asymptote here? Okay, I really wish I could switch colors. Doesn't want to let me because it keeps moving my graph around. Let's see. Okay, there we go. I think I got red now. Yes. Okay, so here, right, my asymptote was on this one, was my y-axis. But when everything shifted, it shifted 4 places over. My asymptote shifts 4 places over too. So 1, 2, 3, 4. This is my asymptote now. Okay, so we can identify that. Okay, I will stop there and we will talk, practice, not really talk, but also talk, and work on logarithmic functions in class. I will see you then.